In this lecture, we want to deal with factors that affect the rate of a reaction. Now, you know from previous lectures that, of course, the concentration of the reactants can affect the rate of a reaction. But we want to deal with what I would call the elephant in the room here, which is basically temperature changes. Now, central to keeping track of how rates change with temperature is an equation called the Arrhenius equation. And what the Arrhenius equation basically shows us is that the rate constant for a reaction is strongly dependent on the temperature. It probably seems intuitively obvious at this point that a chemical reaction should speed up at higher temperatures and slow down at lower temperatures. But we will look at the exact dependence of the rate on temperature and some other factors that need a little more scrutiny. Let's zero in on this Arrhenius equation and define the terms. K is, of course, the rate constant for the reaction we are studying. And as I've said before, it seems strange to say a rate constant will change with temperature because, after all, isn't a rate constant a constant? But actually, the constant part of that only holds as long as the temperature does not change. So as we've said before, once the temperature changes, the rate constant K changes, and so does the reaction rate. The term that comes in the Arrhenius equation that comes before this exponential term, this capital A, is a little mysterious. We're going to talk about that in a few minutes. It's called the frequency factor. And basically, it gives information about how often reactants collide, which we would call the collision frequency, and also an important factor, which is what we call the fraction of those collisions that are of the proper orientation for successful reaction. Again, we'll get to that in a few minutes. Another term that we'll spend a fair amount of time on in this lecture is something called the activation energy. And this is a very important term and a very important concept. This represents the minimum amount of energy, typically given in joules per mole or kilojoules per mole, needed in the reactant collisions in order to get them to react and proceed to products. You can find the activation energy for a reaction by observing how the rate constant K changes with temperature. Now we'll talk more about that soon. That involves making a graph. The thing that you really want to remember here about activation energy is when the activation energy is high. In other words, when this EA term is large, the reaction is slower. Now mathematically that makes sense because when this EA term becomes larger, since there's a negative sign here, this exponential term becomes smaller, which would make the rate constant smaller, which would make the rate slower. So as the EA term gets larger, as the activation energy gets larger, the rate constant will decrease, and so the reaction rate will decrease. Lower values of activation energy would result in faster reactions. R, of course, is the gas constant in energy units, and recall these energy units could be expressed as joules per mole per K or kilojoules per mole per K, and the difference between those two, of course, is a factor of 1,000. And T, of course, is the Kelvin temperature. So let's look at the Arrhenius equation in pieces here, and we want to talk about in order from left to right. We'll talk about this frequency factor A. Now this frequency factor A depends on two things. One, the collision frequency, how often molecules collide with each other. Now of course that would be related to the speed of the reactant molecules. Now if you remember, from General Chemistry 1 when you covered gases. When you describe the speed of gas molecules, a good way of describing that is by using what's called the root mean square speed. And the root mean square speed is simply where you take the speed of every molecule, you square it, you take the mean or the average of those squares, and then you take the square root. Now, for our purposes here, we don't really need to worry about the derivation of root mean square speed. What I want to zero in on is that the speed of the molecules, in other words, what would be related to how often they would collide, is dependent on the square root of the temperature and is inversely dependent on the square root of the molar mass of the reactant molecules. The heavier the molecules, the less often they'll collide because they tend to be slower. But the most important part here for us is that temperature is directly related to the speed of the molecules. So at higher temperatures, the molecules will move faster and collide more often. Let's look at the other thing that the orientation, that the frequency factor depends on, and that's something called an orientation factor. In other words, even if two molecules do collide, it's important that they collide in the proper orientation for a reaction to occur. Now, if you recall this reaction from lecture 2, where we had NO reacting with chlorine to form NOCl, and we found the rate law was equal to K times NO squared times chlorine. And you might also recall from earlier lectures that we have a reaction mechanism box that we haven't talked much about, but it's thought in this box that the first step of this reaction is actually a direct collision between a single NO molecule and a single molecule of chlorine to form one NOCl and a chlorine atom. Now the two figures below show two possible orientations of this step 1 collision. So in figure A, we have NO colliding with a chlorine molecule in a way that that the collision occurs between the nitrogen on the NO and one of the chlorine atoms in the chlorine molecule to form NOCl in a chlorine atom. Now the nice thing about the orientation in this collision is that it's the proper orientation for an NCl bond to form, which is what needs to form in order to start forming NOCl. As an aside, what's curious here is that when we write the formula NOCl, it implies that there's an oxygen-chlorine bond. Actually, in the molecule, there's a nitrogen-chlorine bond. And so this collision is perfect for reaction. And not only that, but the angle of collision here is about equal to the bond angle that's involved in this ONCl complex. If you look in figure B, we have the NO molecule colliding with chlorine with the oxygen end colliding with the chlorine. And since what we need to do is form a nitrogen-chlorine bond and not an oxygen-chlorine bond, when these collide in this orientation, there's no reaction. They just bounce off each other and don't react. So they found each other. It's just that they collided in the wrong orientation. So we say in figure A, this is the correct orientation for reaction. And in figure B, this is the incorrect orientation for reaction. So now you see that this frequency factor has some important information. how often do molecules collide, and of those collisions, what fraction of them are of the proper orientation. This will affect the rate constant and ultimately the rate of the reaction. Let's move down the Arrhenius equation and look at the activation energy. Remember, this E term is just the function E, the exponential function. So this is E raised to the power minus EA divided by RT. So the next chemical term that we talk about here is activation energy. And remember, that's the minimum amount of energy needed in each collision to get the reaction to occur. The activation energy is probably the most important term we're going to talk about in this lecture. So even if the reactant molecules collide at a high frequency, and even with the correct orientation, which is of course what the term A is trying to tell us about, there is no reaction if there's not some minimum energy requirement met, that whole interaction has to occur at a certain energy level. So let's consider step one of the reaction mechanism of the reaction we just looked at, and this would be the collision with the proper orientation. Now, this cartoon actually depicts the molecule slightly differently than on the previous slide. It's the best one I could find, so don't let this bother you. We have an NO colliding with a chlorine with the proper orientation, so then an NO bond is, or excuse me, an NCl bond is formed in the product. So what we have here is 3 steps shown, where we have the reactants coming together and something called an activated complex, where we can imagine that the NCl bond is starting to form and the chlorine-chlorine bond is starting to break, and then it finally goes to products where the NCl bond is fully formed and the chlorine atom rides away. Well, we often look at reactions or describe reactions with energy maps. And what it helps us do is track the overall energy changes and the activation energies for reactions. So here's an energy map for this reaction here, this step one of the reaction mechanism. And you'll notice there's a reactant side, which would be on the left, and a product side, which would be on the right. And in the top of this little hump or mountain or hill, whatever you want to call it, is the activated complex, which is typically symbolized by this double dagger. Now I think I have arrows here pointing this out. These are the reactants. Here's the activated complex. And here are the products. Now if you start at the reactant side, we're at a lower energy than on the product side. And what we have to do to get from the reactant side to the product side is we have to climb this energy hill, go over the top, and then we can kind of roll down the other side. But we have to get to the top. The energy needed to get to that top of that hill is called the activation energy, and it's the activation energy of the forward reaction, because we think of reactions as going from left to right. And here it's known to be 85 kilojoules per mole, and it's the minimum energy required to get a mole of collisions to result in products. In other words, the minimum energy needed to get over the activation barrier, as we call it here, or over the hump of the activated complex. Now, the forward reaction, which again is by default thought of as going from left to right, is overall endothermic because the delta H value is positive. The potential energy of the products is higher than that of the reactants. So interestingly, this overall reaction would require heat input to get from reactants to products because delta H is positive. But the most important thing I want you to see is that it requires an activation energy of 85 kilojoules per mole to even react, to get to the top of this activation barrier. Continuing our discussion of activation energy here, we can actually produce an energy diagram of just a generic reaction. So again, we have a reaction of reactants A and B going to products C and D from left to right. The reaction has to go over an activation barrier, and at the top of that barrier is the activated complex. One thing that I didn't mention on the previous energy diagram is that the x-axis here is defined rather vaguely as progress of reaction. And of course, the y-axis is energy. The progress of reaction is, even though it seems vague, is not a bad label. It's just showing that when you start with the reactants and end up with products, you have to go over this activation barrier. So as the reaction progresses from left to right, we're mapping it out according to the energies involved. So in this case, the forward reaction is exothermic because you start with reactants at this potential energy and you end up with products at this potential energy. So heat energy is lost, delta H is negative, that's fine. The activation energy of the forward reaction is right here, and in this diagram the activation energy of the reverse reaction is labeled. And you might ask, why would we worry about the reverse reaction? Well, we do worry about the reverse reaction sometimes. Let's talk about that. What would the reverse reaction be? Well, logically, it would be C plus D going back over the activation barrier to A plus B. You'll notice that the activation energy for the reverse process is necessarily higher than that of the forward process. We have a larger barrier to get back, to go backwards. And that seems logical. If we want the forward reaction to be favored, we want the reverse reaction to be more difficult. One thing that's assumed here is that the activated complex, which we call CD double dagger here, going backwards, even though we called it AB double dagger going forwards, is essentially the same activated complex. Let's try some practice questions involving activation energy and energy diagrams. So below are two generic reactions. They're both exothermic, and let's see why that is. E plus F going to G plus H. It's exothermic, delta H is negative, because overall the products are at lower energy than the reactants, so energy's been released, going from reactants to products. In this one, A plus B going to C plus D, again, they're both exothermic. This is also exothermic because the energy is lower in the products than starting in the reactants by about this much. And in fact, they've been drawn so they have identical delta H values. So what we want to do is examine both reaction energy diagrams and predict which reaction you would expect to have the larger rate constant. In other words, which reaction would you think would be faster? And give a reason for your answer. Now to do that, we want to assume that the temperature, the collision frequencies, and orientation factors are identical for both reactions. Well, it turns out that the reaction on the left has the smaller activation energy. And so you would say that since we want to remember that K equals AE to the minus EA over RT, that the smaller activation energy would mean this term is less negative, So the smaller activation energy would result in a larger rate constant, which means this reaction would be faster than this reaction. Reactants would go to products more quickly than with this reaction. Let's try another question. And as I say here, this is an interesting one. So below are the energy diagrams, or what are sometimes called energy profiles, for 3 different reactions. Now in these profiles, the exact makeup of the reactants and products is not important. So we don't even give generic equations. If we wanted to, we could mark reactants R and products P, but that's not really necessary because we assume when we draw these diagrams that on the left is the reactant and on the right is the product. Left on the reactant, right is the product. Left is the reactant, right is the product. And so what we want to do here is figure out which reaction is probably the fastest. Another one, which one would have the largest rate constant. And if you compare these, they're all a little different. So for example, in reaction number 1, the activation energy is 15 kilojoules per mole, and the overall delta H is minus 10 kilojoules per mole. So it's an exothermic reaction, and the energy drop overall is minus 10 kilojoules per mole. In the second reaction, the activation energy is significantly higher than in the first reaction, 25 kilojoules per mole, and the delta H is more negative. There's a bigger energy drop going from reactants to products. It's an overall exothermic reaction, and it's more exothermic than reaction number 1. If you look at reaction 3, it seems to have an activation energy that's between these other two, but this reaction overall is endothermic. You can see that the products, final products, are slightly higher in energy than the reactants started at. So overall, it's an endothermic reaction. Delta H is plus 5 kilojoules per mole. So what we want to do here is rank the expected rates of the reactions from slowest to fastest. Well, here are the diagrams. Here are the activation energies and delta H values that we had on the previous slide. And the expected order of the reaction rates should be that rate of reaction 2 should be the slowest. The rate of reaction 1 should be the highest, and the rate of reaction 3 would be in between. Well, you might ask why. You'll notice that I've based my answer totally on the activation energies. I totally ignored the delta H values. So the rate, the reaction that's the slowest would be the one with the largest activation energy, and the reaction that is the fastest is the one with the smallest activation energy. So we expect rate 2 to be the slowest despite the fact that this reaction is quite exothermic. It has the most negative delta H value. Now to some this might seem counterintuitive, but it highlights an important concept that we'll take up in future lectures, which we'll mention here. The overall energy change in a reaction, in this case the delta H, by overall energy change, I mean overall the energy drop or the energy gain going from reactants to products, determines how far a reaction will go until it appears to stop or reach equilibrium. However, the activation energy is what largely determines how fast the reaction reaches that equilibrium point. That is, what we call thermodynamics, or the study of heat transfer, governs how far a reaction proceeds towards products until it reaches equilibrium. But kinetics governs how long it takes to reach that equilibrium. So in reaction number 2, we can say when this reaction's finished, it probably goes the farthest toward products, but it's going to take forever to get there because the activation energy is so high. Now, reaction rates generally increase with increasing temperature, not only because molecules collide more frequently, affecting the frequency factor, but primarily because at higher temperature, a greater percentage of collisions have the minimum energy to initiate reaction. In other words, a greater number of collisions have at least the activation energy to get over that activation barrier. Now we can try to show this with a diagram that we actually used before for a different purpose. So let's look at this diagram. What this is supposed to show is the distribution of kinetic energies of molecules at a lower temperature, that would be the blue line, and then at a higher temperature, that would be the red line. The y-axis here is the number of molecules having a particular kinetic energy. Now, kinetic energy is related to speed. The energy axis is more interesting here because what we can see is that this dashed line is what we consider to be the minimum kinetic energy needed for molecules to react. In other words, it's the activation energy to get over that activation barrier. You'll notice that at lower temperatures, there are some molecules that do have enough energy to get over that activation barrier, but at higher temperature, a much greater proportion of molecules have the minimum kinetic energy to get over that activation barrier because more molecules have higher energy. If you actually look at the areas here, you'd find out that the area underneath the red here is larger than you think because the blue area obscures some of the red area. Bottom line here is that at higher temperatures, a greater percentage of the molecules have the minimum energy, the activation energy needed to get over that activation barrier, which increases the rate constant and increases the reaction rate. Now, the Arrhenius equation can be used along with appropriate experimental data to actually determine the activation energy of a reaction. This is going to involve making a graph. If you look at the original form of the Arrhenius equation, it's right here. And what we're going to do is manipulate this and try to get it into the form of a straight line. To do that, we're going to take the natural log of both sides of this equation and rearrange. So we'll take the natural log of k, that's what's on the left, and then the natural log of this whole term here, a e to the minus ea over rt. If we do that and leave ln of k alone here for a minute, we figure out from what we remember about logarithms is that this term here is equal to the ln of a plus the ln of e to the minus a over rt. Because remember, the natural log of a product is the sum of the natural log of the pieces of that product. We'll leave ln of a alone for a minute here, and we'll realize that when you take the natural log of an e function, we can say they kind of cancel each other out. So all you're left is this term here, minus ea over rt, which I've rewritten right here. And then, just for cosmetic reasons, I'm going to bring that minus sign out in front. So we have the ln of k equals the ln of a minus ea over rt. We can do a little more rearranging by taking this ln of a term and putting it on the other side, and then just moving some parentheses. So this equation right here is equivalent to this one here. We have ln of k equals minus EA over R times 1 over T plus ln of A. And what we've done here is we've gotten the Arrhenius equation in the form of a straight line. You can see that y would be ln of k, the slope would be minus EA over R, x would be 1 over T, and the intercept would be ln of A. So if you can measure the rate constant K at several different temperatures T, you can construct a graph where the y-axis is ln of K and the x-axis is 1 over T. This should look familiar from a previous lecture on vapor pressures. You can get the activation energy from the slope of the best fit straight line. So let's try an example. We can use our familiar reaction, NO plus Cl going to NOCl, where the rate law was right here. And let's suppose someone measured the rate of this reaction at 6 different temperatures and used the rate data in the known rate law to calculate K at each one of these temperatures. So we have 6 temperatures, 6 different rate constants. You'll notice, of course, that the rate constants go up when temperature goes up, which is what we'd expect. Now, in order to get this in the proper form, we're going to have to convert the Celsius temperature to Kelvin and take the reciprocal. And we're going to take the natural log of K, and we'll temporarily drop the units. And we get a table of data that looks like this. 1 over T for 1 over temperature in degrees Kelvin, and ln of K. Now, if you're observing closely here, you're going to see I'm carrying 1 extra digit than I should probably if you're considering significant figures, and I very snidely said I'm doing this because I want to at this point. And there's 4 digits after the decimal point in the ln function. That's from the 4 significant figures in the K. So the straight line form of the Arrhenius equation, remember, is ln of K equals minus EA over R times 1 over T plus ln of A. And our x-axis will be 1 over T, and our y-axis will be ln of K. So let's see what the graph looks like. Well, here's our data. X-axis 1 over T, I've plotted right here. Y-axis ln of K, I've plotted right here. We get 6 data points, and I fit it with a linear trend line, and the slope of the line is minus 2281.7, and the y-intercept is 10.63, and you can see that's a pretty good fit. So remember, the slope that we get here, according to our rearranged Arrhenius equation, is equal to minus EA over R, and the intercept is equal to the ln of A. So let's solve for EA, which is the most important part. The slope is equal to minus 2281.7 K, that would be the units of slope here. We're going to set that equal to minus EA over R, because that's what the Arrhenius equation says it should be set equal to. We'll cross multiply, in other words, take R times our slope, and we can't forget our minus sign here. And if we substitute 8.314 joules per K per mole and get rid of the minus signs, because there'd be minuses on both sides of the equation, so they'd cancel out, and you end up with an activation energy of 18.97 kilojoules per mole. Now, absent any other data to compare this to, this activation energy probably doesn't mean all that much, but that would be the minimum energy needed to get over that activation barrier in those energy diagrams. But the most important thing here is you can see how activation energy is determined, and that it's a positive number. Now, in case you're interested, and it's okay if you're not, we can calculate the value of A. And remember, ln of A equals 10.63, And we can take the e of both sides, the exponential of both sides, and we'd end up with A being equal to 4.136 times 10 to the fourth molar to the minus 2 seconds to the minus 1 for a value for that frequency factor. Now, there is another way we can take advantage of the straight line linear relationship between ln of k and 1 over t afforded by this Arrhenius equation. So let's try to do that. Now, if you went into the lab yourself with the intent of measuring the rate constant k for a reaction at several different temperatures, then making a plot of ln of k versus 1 over t in order to determine the activation energy, you would most likely want at least 5 data points to get the best linear fit. We just use 6 data points. You would also, of course, strive to measure the rate constants over the broadest range of temperatures possible to avoid clustering your data over a narrow range of temperature. Now, let's assume you need a quick estimate of the activation energy for a particular reaction, and that you're confident enough in your lab skills and the design of your experiment that you believe any error associated with your measurements would be small. Why not just take 2 measurements and assume a straight line relationship between the 2 pairs of results, the ln of K1 at T1 and the ln of K2 at T2 at the second temperature? Well, that means we probably need to derive a single equation containing 2 different rate constants and 2 different temperatures and, of course, the activation energy. So let's try that. We could write the Arrhenius equation in the linear form for K1 at T1. So this would be the rate constant K1 at temperature T1. If we change the temperature, of course, we'd get another rate constant at that temperature. So we have 2 Arrhenius equations describing 2 different rate constants at 2 different temperatures. Of course, EA is the same for both because it's the same reaction. R would be the same. We're going to assume that A will stay about the same. Now, let's do what appears to be just some random algebra. We're going to subtract one equation from the other. So I'm going to take this equation right here and put it in this big brackets, and then I'm going to subtract the other equation in these big brackets. And when we do that, we'd say, looking at what's on the left of the equation sign, we'd have ln of K1 minus ln of K2. And what's on the right of the equal sign, I should say, would be this term here from the first Arrhenius equation minus the second term here from the second Arrhenius equation. Well, at this point, I'm going to remember that the ln of K1 minus the ln of K2 is equal to the ln of K1 over K2. I'm also going to take the brackets off of these here and write the first term right here and the second term right here. So we have minus a minus EA over R, so that turns into a plus, and we have minus this plus, so that turns into a minus. And what we have here, as we've assumed that the frequency factor won't change that much, these 2 terms, the 2 ln of A terms, cancel out. And what you're left with is an equation that looks like this. And the nice thing about this equation, if you believe the algebra and believe the equation is useful, and that our assumption that A hasn't changed too much isn't too much an error, we have an equation with a rate constant K1 at temperature T1, a rate constant K2 at temperature T2, and an activation energy. So if you know 4 out of these 5 variables, you can calculate the unknown variable. So we have 5 variables, 2 rate constants, 2 temperatures, and an activation energy. If you know 4 out of the 5, you could get the other term. What we're going to do is give you information, since we already have it, for 2 of the rate constants and 2 of the temperatures. We're going to calculate an activation energy, again with just 2 data points. So here's the data table that we used before, and what we're going to do is, instead of graphing it, we're just going to pick 2 points and try to use this form of the Arrhenius equation to calculate an activation energy. So our 2 points here are K1 of 17.23 at a T1 of 20 degrees or 293.15 K, and that would go right here. K1 would go here, T1 would go here, and our K2 will be 43.87. K2 would go here at temperature T2, 60 degrees C or 333.15 Kelvin. T2 would go here. And of course, we remember what the gas constant will be. So substituting in the numbers, we have our 2 rate constants, we have our 2 temperatures, and the gas constant. The natural log of this ratio would be the natural log of this number here. This ratio, units cancel out, so you get this number here. And if I take 1 divided by 333.15 K, I get this. And again, for 1 over 293.15 K, I get this. If you take the natural log of 0.39275, you get this value. If you subtract these 2 terms from each other, you get this value. So let's finish this up on the next slide. I'm going to take this equation and move it over to the next slide. So there it is. What I did here was cross multiply 8.314 joules per mole per K by this number over here. So we end up with minus 7.770 joules per mole per K equals what was left on the other side. I'll divide both sides by this term, and I get this, and working this out, we get an activation energy equal to 18.97 kilojoules per mole. This is just using 2 points, assuming the straight line relationship between them. And if you compare this value to that obtained from plotting a graph of ln of K versus 1 over T for 6 temperatures, you get the same value. Now, if you're too tired to look back at that slide, it is the same value. So you might ask, why would anyone ever make measurements at more than 2 temperatures? Which is a good question. And the answer to that is, in the real world, your chances of introducing error into just 2 measurements is quite high. So it's good practice to take several data points and then fit a best straight line to those points if a linear trend is expected. And that usually ensures a more accurate value of the activation energy.